Good day, everyone. I want to apologize the last time I was unable to upload this lecture because I didn't know that the recording stopped. So I had to do this one to upload for today's lecture. This is like a repeat class for everyone because I have to do everything anew. So today we are looking at rotational motion. Now, the last class we looked at circular motion and we applied them to solving some problems. We looked at circular motion, orbits, and gravity, and we're able to establish that orbits is the equivalent of projectile motion on a plane or one-dimensional motion. And also we talked about the gravity and the gravitational laws, Newton's law of gravity obeying the inverse square law. And we're able to establish the relationship that the force is actually proportional to the product of the mass to mass and inversely proportional to the square of the radius. And today we want to advance further into another kind of motion that is common to our everyday life, which is rotational motion. And as you know, in chapter 7, like the reading of the course is, we take each chapter per week. So we'll be covering 3 major blocks. We'll talk about the rotational kinematics, we'll talk about torque, and rotational dynamics. We also establish the relationship between each of these terms to their equivalent in linear and circular motion and how they are unique to rotational motion. Okay. So our goal is primarily to understand the physics of rotation or the physics of rotating object and how to maximize that to our understanding of modern science. Okay, so we want to begin by describing the circular motion and rotational motion. We have talked in depthly about circular motion in our previous last 3 classes, and want to quickly begin with the rotational motion. The rotational motion is actually the motion of object that spins about an axis. Okay. The circular motion we described object that is moving in circle, but in this case, it is the motion of object spinning about an axis. Or we can say motion of an object spinning about its axis. All right. So we see the image here. It's the image of a wind turbine. We see the blades. The picture is blurred because they are in motion when this picture was taken. And we can see that the blade is blurred on the tip more than towards the axis or the center. Okay, and that means that it's moving at different speed. The speed at the tip is different from that of those or points closer to the middle. Right? So we see that the description of this kind of motion is really kind of dynamic because it is spinning about its own axis and at the same time taking a circular motion. Okay, so we'll see a combination of the blade spinning about its axis and also the motion of the uniform circular motion. This description made us to advance further into classifying this kind of motion in rotational motion with new quantities that will be defining, because there's no way we can understand the dynamics of this kind of motion without defining these new terminologies. such as the angular position, angular displacement, angular velocity, and angular speed. Okay, we'll be looking at each one of them and how we apply them to solving problems. So let's quickly look at angular position, which is the first term we want to look at. Angular position for circular motion is it's convenient to use the angle theta to describe the position of an object that is in a rotational motion. All right. Now we use angular position to better describe the position of object. Why in other cases we use in like in the plane, we try to use just the coordinate or the axis to describe the position. But when it comes to the circular motion and the description of it in relation to rotational motion, we use what we call the angular position. Angular position primarily describe the particle's location, and the angle theta is called the angular position, as we can see in this image, this particular image called angular position image. All right. So we see the angular position, which is the angle theta describing the position. We are taking the position from the positive x-axis. So this motion is proceeding in this direction. So we have this distance moved from the x plane as s, which is the arc length. And then we'll have the particle here, the radius of the circle, the theta here as the angular position, and then the origin as the center of the circular motion. Now the theta, angle theta is always measured in rad. And how is this related? We know in terms of plane, the general formula for speed is changing distance over time. We'll be taking some of those terms to understanding how we arrived at the formulas we are using in this particular discourse of rotational motion. So we always have to measure angular position in radians. And the theta is described as the arc length, which is x, over the radius of that circle. So if we make as the subject of formula here, we'll have theta r, and that's what we have here. And this relationship is only true if our theta is measured in radians, never in degree or not in degree. Okay, so if they give you the value in degree, you have to convert it to radian. And this is the relationship for just the path motion of the particle. What happens if the motion completes, if the particle completes a full circle? We know the circumference of a circle. So the distance covered, which is the arc length, will be the circumference of a circle, which is 2 pi r over the radius of that circle. So this take care of this. That is how I arrived at theta equal to 2 pi rad for full circle. And the angle of full circle is 360 degrees. So this relationship is what helped us to get the conversion for rad to degree. So in converting rad to degree, we just divided 360 by 2 rad to give us 57.3 degrees. So 1 rad equal to 57.3 degrees. Okay. So we'll proceed to describing another term, which is the angular displacement and angular velocity omega. We use omega, this coily W kind of, to represent angular velocity. Now, We know the definition or the expression of angular of displacement when we discuss the linear motion, and we know what the formula also for velocity. We're just going to borrow the same concept, but in this case, we're always talking in terms of the angle because we use the angle to describe the position of the particle per time. All right, that's why the name angular is always attached to the quantity that we're describing. So let's look at the particle 1, 2. We see that in the particle 1, a particle with a small angular velocity, omega, undergoes a small displacement as well. All right, so we see this particle 1 undergoing the displacement of quarter this circle in 5 seconds. But let's look at, in comparison with particle 2, it has large angular velocity and it undergoes a large displacement. All right, we know the definition of displacement in our linear case. Displacement is changing speed over time. Right, so, and we know that velocity is changing displacement over time. So if we say angular velocity in this case, using the symbol omega to represent angular velocity, is simply angular displacement over time interval. So we see the angular displacement for each of these motion. So the change in the angular displacement over time will give us the angular velocity. Okay. So the same way we also studied the position in terms of positive or negative, the direction of velocity in the linear state, that we'll also do in this case. When, let's look at particle 3, when the particle is taking a counterclockwise rotation, it is assumed to be going in the positive direction. Why? You remember that we said when we're describing the position that we always describe it from the positive s-axis. So if this is a positive s-axis, it's going this way in the positive s direction or positive s and y direction. You can see we say it is positive. But when it's going this way to the negative s direction or negative s and y direction, we say the motion, which is a clockwise motion, is negative. So that is how we know the sign of angular velocity. And angular velocity also is a one-dimensional, angular velocity is in one dimension, just like your velocity on the s-plane. All right. So let's quickly take an example from the to drive home the short discussion we just had. Example 1. Find the angular velocities of particle 1 and 2 in the figure above. Now let's look at the figure again. Particle 1 covered quarter of this in 5 seconds, while particle 2 covered half this circle in 5 seconds. Right? So if we adopt the formula that says angular velocity is equal to change in the angular displacement over displacement change position. Remember that theta is actually angular position, so displacement is in change in position. All right, so angular displacement over time. But we know that theta is equal to 2 pi, which is for one complete revolution. So the particle 1 covered just 1/4, which means it covered a quarter of the revolution. So 2 go into here and 2. So we'll have that particle 1 cover the distance pi over 2. So that's the pi over 2 rad you have here in 5 seconds, which is the 5 seconds. And when pi is a constant, all right? So When you divide that, you get 0.314 rad. But for particle 2, it covered half the revolution of that circle in 5 seconds. So half, so half 2 take care of 2. So particle went pi rad distance, right? So that's why we have the pi rad here. And then it did that in 5 seconds. So we get the angular velocity to be 0.628 rad. Okay? But we know that the full expression of change in position in terms of displacement is equal to the final minus the initial, just like as we used to express it for both the linear and the circular discussion that we've had. So this is actually the definition of our angular displacement for uniform circular motion. So let's take an example to see how we apply this to solving problems. A small steel ball rolls counterclockwise around the inside of a stationary 30.0 cm diameter roulette. Okay. The ball completes exactly 2 revolutions in 1.2 seconds. A, what is the ball's angular velocity? And B, what is the ball's angular position at t equal to 2 seconds? Assume that the position is starting from 0, okay, which is the initial position is 0. So how do we begin solving this problem? For A, it's straightforward. It says, what is angular velocity? So we just bring in the formula for angular velocity. Remember the statement. It said it covered 2 revolutions. So 1 revolution is 2 pi. And it did that twice. That is how we have this. Okay, divided by the time it took to cover those that distance. So we'll have the angular velocity to be 10.47 rad. Okay. Then we also have the question that says, what is the angular position at 2 seconds? So we assume, because we have been told to assume that the initial will be 0. So how did we get this equation that we're using here? W is equal to change in theta over change in time. So if you make change in theta the subject of formula, you will have W change in T. But also we know that change in theta is, we also know that, let me use this base, change in theta is equal to W change in time, which means theta final minus theta initial is equal to W change in time. So we'll have theta final, which is what we are looking for, is equal to, move this theta initial to cross the sign of equality, becomes positive, plus W change in T. This is 0, already given as 0. And then we'll have the value of this one in our first question. And we'll have the time given to us at 2 seconds. Okay. So that is how we arrived at this expression. So substituting directly, what is 0? This one is given as 0. W from this, we have 10.47, then the time 2 seconds. So we got 20.94 rad. Okay. But remember the question says, what is the ball's position? How do you describe this in terms of revolution of the circle. What position would this give us? So if we have the final position to be 20 rad, to take this 20 rad in terms of the revolution covered, what we did was to say 20.94 all over 2 pi, because that is 1 rad. So when we did that, we got 3.333. Okay. What this simply tells us is that this has completed 3 revolutions and is 0.333 into the 4th one. So if this is 0.33 rad, how do we know this position in terms of degrees so that we can better explain it in the quadrant? All right. So we have 3 revolution, which is the 3 rad, and then this rad. Okay. So 3 revolution completed. Multiplying this to this, will have, let's multiply these two. This will multiply 3 and this will multiply this. Okay, so we'll have 2.9 rad, and we want to convert this 2.9 rad to degree. We just multiply by 57.3 degrees. So we'll have about 120 degrees. So if we make this quadrant, this is 90. So 120 degree will be about this side. So it is actually the position of the particle will be at the middle of the second, not the first quarter, into the half or the second quadrant. Okay, so we'll now describe or explain the answer number B, that at 2 seconds, the ball has completed 3 revolutions and has gone 2.09 rad into its 4th revolution, or 120 degrees into its 4th revolution. So an observer will simply say the position of the object is at 120 degrees. Okay. You take note of this because that's one of the exercises we do in the class. All right. So let's look at the angular speed in terms of period and frequency. Okay. Angular speed in terms of period and frequency. We have already described that angular speed is equal to change in this over change in t. Now, we first of all remember that this theta is actually equal to 2 rad. And change in t, which is 1 revolution when it's 2 rad, is the definition of period, which is the time taken to complete 1 revolution. So we can say change in t is equal to t. So if theta is equal to 2 rad, change in theta, and change in t is equal to t, we can actually put it in this equation. But remember also that frequency is equal to 1 over t. So we can replace this 2 pi dot 1 over t will now give you 2 pi f. So this is actually the expression that relates the period, frequency, and angular velocity. All right, so let's quickly take an example on how we can use that to solve problems. A crankshaft in your car engine is turning at 3,000 revolutions per minute. What is the crankshaft angular speed in rad? First, when we're given values in revolution per minute, we should convert it to the basic or SI unit, which is rad per second, so that we'll be able to express our answers in the standard unit. So we'll convert the revolution per minute to revolution per second. So 3000 rev per minute times 1 minute over 60 seconds. Minute take care of minute. We just divide 3000 over 60 to give us 50 revolution per second, which is also regarded as frequency. So we'll have to adopt the formula that shows the expression of frequency because the question says we should look for the angular speed. All right. We use the symbol angular, the same symbol for angular speed and angular velocity because speed is this, velocity is actually speed with a defined direction. Okay. So putting the parameters into a formula, we have 2 rad, then we have the frequency. Multiplying pi is a constant. Multiplying these two, we have 314 rad per second. That is the angular speed. Okay, so let's look at what these concepts, we know it very well. I want to assume because almost everybody got it right when we treated it in linear cases or in one-dimensional motion. In linear motion, yes, and in one-dimensional motion. We're able to convert velocity or position time graph to velocity time graph, also convert velocity time graph to position time graph, and also derive from position time graph the acceleration time graph. So we know this topic very well. We're not going to dwell so much on it. So the slope of a position time graph will give us velocity. In the same way, the angular position time graph, the slope of it will give us angular velocity time graph. So we'll have the position time graph here. The slope will give us the velocity time graph. And the way to express this is to take the slope here, the same way we converted in when we're treating linear motion. It's the same way we do it here. Take the slope and then stretch over the time to get the velocity time graph. So I'm not going to dwell so much on it, but I'll advise us to check the example 7.4 of our test, this example 7.4 of our test. So we also want to point out the relationship between speed and angular velocity. Now, V was given before in circular motion description as over T. Remember this expression? But we also know that W is equal to 2 pi R over T. So that means we can substitute this for W. So we'll now have V to be WR. Okay. So this is how we derived this expression. All right, so let's go to, before we start discussing the rigid body, I'd like us to quickly look at something. I'd like you to put in your answer in this pool. Let me share a new page. One moment. Share, stop sharing. Share new screen. Just give me one moment to do that. Okay. I think my screen is not shared. Share. All right. Now, I'd like us to put our answers in this pool. Okay. If you agree that 2 pi Sorry. The question is, which particle has the angular position? Is it particle A, B, C, D? Remember that one revolution is 2 pi. So how do we get the final answer? 5 pi divided by 2 pi will give you how many? 2 remainder a pi, right? So we'll have 2 revolution, and then we'll also have 2 remainder 2 pi, 1 pi. Okay, we'll have pi over 2 because the pi that will be remaining, if you divide to know the position of the revolution by 2 pi, okay, we'll have divide by 2, not 2 pi, sorry. We'll have just 2 pi, which actually gives us 1/4, all right? Because half of this is pi, and pi over 2. So the answer is A. 2 revolution remaining 1 pi over 2. The pi over 2 is quarter pi over, because I believe we understand how we arrive at A. Where is my eraser? How many simply how many revolution are we going to get in 5 pi? We will get 2 revolutions, which is 2 pi dot pi. All right, 2 pi dot pi will give us 5 pi. 2 revolution, that's the meaning of this. So to know the final position of that angle, the remaining, which is the 1 pi, actually we know that 2 pi will give us 1 complete revolution. Okay, so the remaining 1 pi all right. I'm looking forward to seeing our answers in the pool. All right. So the pi divided by 2, we divide each one by 2 pi, and we will have I give us 2 minutes to get that. Put your responses. Okay. Okay, most of us chose A as our option, which is the right answer. So A is our final right answer, and this is how we arrived at A. We just said 5 pi. This pencil is just acting up. All right, my pencil. So just say 5 pi divided by 2 rad, which will give you 2 revolution and pi over 2. Okay. So we have 2 revolution, which is 2 pi rad plus pi over 2 rad. Pi over 2 rad will give you a quarter. All right. So that's how we arrived at A. So I'll stop sharing this screen. Let's go back to our class. And most of us give the reply to be the correct one, which is A. Okay. Can we still see my screen? Yes. All right. So let's quickly run through the second half of our class, which is the rigid body. The rotation of a rigid body. What do we mean by rigid body? A rigid body is an extended object. Note this, whose size and shape do not change as the body moves. Okay? The size and shape do not change as the body moves. Such object is what we refer to as rigid body. A typical example of rigid body is the bicycle wheel. We see it move from one place to the other, but the size and shape does not change. And the unique thing about rigid body is that what we used to know as our particle model becomes inadequate to understanding the motion of this very unique, let me use the word complex kind of motion, where we have a rotational motion at the same time with other types of motion, which we will look at immediately after this slide. So we tend to ignore our understanding of particle model when we start describing rotational motion because it cannot adequately describe the whole system. As reason being that different parts of the body, they are moving or taking a different motion, so you cannot summarize the whole motion system into a dot like we do in particle model. Okay, a typical example of what I'm trying to say is the turbine that we saw in the first case. You see the blade or the particle at the tip moving at different rate or speed from those particles closer to the center of the system. So we emphasize that we do not use particle model to describe rotational motion. Okay, so how do we describe rotational motion? We have three basic types of motion in a rigid body or in a system of body undergoing rotational motion. We have one, the translational motion. Two, we see the rotational. Three, we see the combination of both translation and rotation as the object takes a particular trajectory. Okay, so we see the object as a whole move along a trajectory, but does not rotate. Okay, we have parts of the object that is moving along the trajectory, but it's not rotating. We also have parts of that object, rigid body, rotating about a fixed point, just like the wheel. And then every point on the object moves in circle as you look at some part of it. Then we'll have a combination, just like the wheel in motion, of the object that is rotating and at the same time is translating or taking a curve, moving and rotating at the same time. So in general, we are saying that the rotating rigid body have the same angular velocity. So we can refer to the angular velocity W of the wheel. Okay, so we'll refer to the angular velocity W, which is omega. Let me not be using the word W anymore. Pardon me, please. Angular velocity omega of the wheel. All right. So if we're using this typical example of the bicycle wheel, we can just refer to the angular velocity of the system because at every point of a rigid body, it will have the same angular velocity. So we can just use the word angular velocity to describe the motion or the velocity of the system because at every point we will have the same thing. Now, we have another term we want to look at today, which is called the angular acceleration. We use the angular acceleration in the scenario of non-uniform circular motion. Okay, so it is a system where we can describe that the acceleration, there's actually acceleration. Remember what you said about linear or a uniform motion, acceleration is zero, velocity is steady. So it's the same concept that we're bringing into this one. The angular acceleration for particle, for the non-uniform, for particle in a non-uniform circular motion is given by the same pattern, change in velocity over time, which is change in angular velocity over change in time. All right, and we use the symbol alpha to represent angular acceleration. So we see the same analogy of the rigid of the bicycle wheel in a rigid body. The angular velocity is changing. That is, we can see from the dot how the distance is getting wider to indicate that there's acceleration in this direction. Okay. So we can only describe angular acceleration for non-uniform circular motion. Now, how do we determine the sign? The same way we did before. We remember when we're treating it in linear, we said that when velocity and acceleration is in the same direction, the particle is speeding up, and when they are opposing, it's slowing down. And then we also said that the direction of acceleration determines the sign. So if we look at this, let's look at the ball now. Look at the direction of acceleration in these two cases. We can see that the direction of acceleration is moving to the left, right? Acceleration is moving to the left. So acceleration is positive. So we see acceleration moving to the left here like that. This particle is accelerating. But when we see it speeding up, we see the vector, velocity vector in the same direction, and we see acceleration in opposite direction to the velocity vector. So you see that we're actually taking the same concept. In this case, acceleration. Look at the direction of acceleration here. And the acceleration is moving this way. So we see when acceleration is taking a clockwise motion, we say acceleration is positive. But when it's going counterclockwise, we say it is negative. So that is what you should note. When acceleration is going, sorry, I messed it up. When acceleration is going counterclockwise, it is positive. When it's going in a clockwise motion, it is negative. Okay? Counterclockwise gives us positive angular acceleration. Clockwise motion gives us negative angular acceleration. So we'll look at example 7.6 to buttress that. Okay, so this sheet is simply the comparison of what we see in linear motion and how it relates to the circular motion. So we'll have velocity change in distance, also change in position over time. This is velocity in terms of linear. This is velocity in a circular angular motion. So we see that it's the same equation, but with unique terminology as it relates to the kind of motion we are describing. Now, I'm just going, we won't dwell on this. We're just showing us also that we can actually get from the velocity time graph, that is angular velocity time graph, we can also get the acceleration time graph. And we know how we got this from this. I advise you to look at this example, but we know exactly how. The slope of this gave us this. And we know how to convert that. So let's look at the last thing we want to see today. It is the term tangential acceleration. Tangential acceleration measures the rate at which particle speed around the circle is increasing. Okay, so we use the symbol T, AT to represent tangential acceleration because we have to make a comparison with the centripetal acceleration. Centripetal acceleration in the description of uniform motion, we always stated that it is the acceleration that is always pointing towards the center of a circle. But for non-uniform motion, we will find another kind of acceleration which actually describes the speed of that particle around the circle. So we'll see another acceleration that is appearing like the component of the acceleration that is pointing towards the center, which is the centripetal acceleration. And we describe that as the tangential acceleration. So tangential acceleration, AT, is also a vector, and it causes the particle's speed to change. Okay, so there is a tangential acceleration only when the particle is speeding up or slowing down. Okay, so we see the particle speeding up, we see the velocity vector, and we see this one as the acceleration. The acceleration is, we call it tangential because it is always at the tangential direction to that acceleration that is pointing towards the center of the circle, which is the centripetal acceleration. So the formula for tangential acceleration is also the same, change in velocity with time. So we'll have, remember we've already established that V is equal to WR. So that's how we substituted it into this. And then we know that change in W over change in T is equal to acceleration. So we can actually, it's equal to angular acceleration. We can actually bring out angular acceleration from, which is alpha, from this expression to give us the relationship between tangential and angular acceleration. So we can go through checking understanding. We emphasize that all position, okay, in this kind of system have the same angular acceleration. So when we ask that the two coins rotates on a turntable, coin B is twice as far from the axis as coin A. Does it mean that the angular velocity of A is twice that of B, or angular velocity of A and B are equal? B is the answer because we said at every point in a rigid system, the angular velocity is the same. So we'll have B as the answer. Thank you. So I stop sharing.